Should we start? First of all, sorry for the slight delay. I'm Suyash from Ingoniama, and we are going to do a workshop on Icicle. Am I audible at the end of the room? A little bit louder? Okay. So I'm Suyash from Ingoniama, and we are going to take a look at one of our product, which is called Icicle, which is a GPU acceleration library for cryptography, and more generally we also plan to add other backends like the Metal GPU, or in future hopefully ASICs. So I'll give a brief introduction before we start. So I'm on the research team at Ingoniama, mainly working on trying to come up with like new algorithms, not just focused on accelerating different cryptographic techniques, but also more generally applicable to SNARKs or STARKs in general. The software team at Ingoniama is the main architect and the main brains behind Icicle. So bear with me if I'm not able to answer some of the technical stuff, but I'll try my best. So we'll start with so here's how we'll like schedule this workshop. We'll start with the bit of introduction of what is Icicle. Then we'll talk about why do we need Icicle, what's the promise of Icicle, and how people are using Icicle. And then we'll see some of the features of Icicle, and what's different with Icicle that we can expect to make the lives of developers easier. So let's start with why Icicle, and then towards the end we'll do a bit of hands-on coding session. We'll try to go over a few examples and then try to do a quick exercise. I'm sure Invisible Garden has been great in the sense that you guys already might have discussed a lot of cryptography, some check, been following things on Twitter. So hopefully it should be a fun exercise at the end of the session. So let's start with why Icicle. Everyone knows this, hopefully everyone knows this, that SNARK proof generation or STARK proof generation is generally very slow. And fundamentally the reason is you are trying to prove something so that the verifier is able to verify the validity of your statement pretty quickly. The aim of STARKs and SNARKs is to have a succinct verifier. The S stands for succinct. And therefore, if we want to make the verifier succinct or the verifier very fast in the action of verifying a particular statement, the prover has to bear the burden. That's fundamentally the reason why the provers are generally slow. But still we know zero knowledge proofs are very powerful, so we need to accept this flaw or accept this shortcoming that the prover is generally slow. Then the next question is, can we make the prover faster? And that's what the last 10 years of research in SNARKs has been focused on. And different teams, different people, academia, industry have been working on trying to accelerate ZK SNARKs from a theoretical as well as practical point of view. One thing that we can realize with these SNARKs and STARKs is these zero knowledge proofs, these family of zero knowledge proofs contains some primitives that can be parallelized, and we'll see why quickly. So typically you start with a witness trace or a witness table. That's what I'm showing here. I'll not go into the details of what witness means or how we generate this witness. That's a different topic. But assume this is a witness trace. So this is basically a succinct representation of whatever data you want to prove. Let's say I want to prove that I am currently in Thailand. So everything related to my location, everything, all the secrets, all the public information is included in this table. So this is my ground truth. Once I have this ground truth, I can run these SNARK or STARK algorithms, prover algorithms, to generate proof, which is a succinct proof that encodes this information. And if I give you that proof, or if I give that proof to any authority, they can quickly verify if I'm saying the truth or not. So the point I'm trying to highlight here is, based on the size of this ground truth or the witness, the prover complexity is order n or order log n, where n is the size of your trace or size of your witness. And order n as well as n log n, both are pretty slow. The prover computation depends on the size of your witness. And eventually everything in SNARKs or STARKs or modern ZK SNARKs boils down to polynomials. So what you do is you take this witness, you construct a few polynomials, and then you show the relation between those polynomials is true or it holds. So therefore, as soon as we have polynomials, there is a limited set of computation that people do with polynomials in the context of SNARKs and STARK proof generation. And we already know some of these primitives are the MSM, multiscalar multiplication, FFT, and sum check. Now in the context of polynomials, MSM is used to commit to a polynomial. You might have heard KZG commitment scheme that uses multiscalar multiplication. FFT is also one of the most popular primitives, which is used in polynomial transformation. So if you want to go from evaluation domain to coefficient domain and other way around, you need FFTs. And the third primitive, which is not new, but a lot of people have started looking into this third possibility, which is called sum check. It's again an operation that you do with polynomials, and all three of these operations, the first and the third, are linear in the size of your polynomial, in the degree of your polynomial. And FFT is n log n. So why do we believe that SNARK or STARK generation is parallelizable? Because some of the main primitives like MSM, FFT, and sum check are basically polynomial operations, and once you have a polynomial operation, there is scope for parallelizability. Any questions so far? Okay. So then we realize that there is immense scope for parallelizability in proof generation of modern ZK SNARKs. So then the obvious next step is, can we parallelize these operations, and can we offload these computations as much as possible to GPU? Now why GPU? Because GPU is readily available resource that we can use without having to go through the process of designing and then taping out an ASIC and so on. And GPU is already pretty popular with machine learning related computations, and the idea there is also very similar. You basically do lots of matrix operations using GPUs. And if you think about a matrix, it's nothing but a 2D polynomial or a bivariate polynomial. So realizing that you can use GPUs to accelerate polynomial computation or accelerate these primitives that work on polynomials was the next obvious step. So here's what happens. Let's say I have a host, or let's say I'm a developer. I write some code. I write a SNARK or STARK prover in my language, in the language of my choice, CPP, Rust, Go, whatever. Now, what I want to do is I want to leverage these bunch of GPUs, offload computation as much as possible, but at the same time, I need to be aware about three things. One is device management, in the sense that if you have multiple GPUs, which task is to be offloaded to which GPU. That's something we need to take care of. The next thing we need to take care of is the data transfer, because data transfer between your computer and the GPU is generally considered to be expensive, because the size of the data that we are looking at here is typically pretty large. If we look at like typical SNARK circuits, you need the bottom range is like 2 to the power 16, and then the higher range could go up to 2 to the power 26, which is pretty large amount of data. So we also need to take care of the data transfer between the two devices. And then the third thing is, of course, related to data transfer, which is memory management, which is again related to the last point, that if you have if your witness polynomial is very large, and if your GPU memory does not allow you to store all of that witness data, how do you manage to perform these primitive operations like MSM or NTT or sum check if you can't fit your entire data into the GPU memory? So these three things is what we need to basically have answers for: device management, data transfer, and memory management. And this is what Icicle tries to simplify from a developer point of view. And the objective of Icicle is to keep all of these three things in the backend, so that the developer doesn't have to worry about manually managing any of these. Also, one thing you might have noticed is I said you can write your prover in any language. For now, we support 3 languages: C++, Rust, or Go. So therefore, developer also doesn't have to worry about learning a specialized language for writing fast SNARK provers. You can basically use Icicle if you have your prover written in any of these 3 languages. And we'll come to what new languages we are working on for future. So therefore, what Icicle tries to do is let the developer focus on math and leave the acceleration part to Icicle. Because if you realize the math that we do in cryptography or SNARKs is not that difficult. It's not. People have a different opinion. People think that all of this is moon math, but in my opinion, the actual math that we are doing is pretty straightforward: multiscalar multiplications, entities, or whatever, or even sum check. So therefore, our objective is for developers to focus on the code, focus on writing math, and not worry about making the prover faster. So quickly, I'll go over few features or main points of Icicle. So Icicle development started a couple of years back, and our aim was not to build a library specifically to accelerate ZK SNARKs, but it was more of an in-house effort to try and figure out how we can leverage GPUs to make computation faster, make SNARK proving faster. And soon we realized this is a problem that's faced by a lot of teams. So then we decided to package it in form of a software that is easy to use for the developers. So Icicle is basically a high performance cryptographic library for accelerating ZK SNARKs. The objectives, or like what we try to achieve, the first point is versatility, which means we want to be able to support multiple hardware backends, not just GPU. We also want to support, let's say, web GPU or the Metal GPU on Macs. More so because client-side proving is becoming much more relevant these days. We want Icicle to be efficient, which is specifically customized for ZK computations, and a lot of the efforts of our research team goes into coming up with new multiplication techniques or improving the efficiency of low level operations so that we can make Icicle better. We want it to be scalable, and basically what this means is we want the friction to be minimum for the developer to use Icicle in whatever project they want to. As I said, we already have super optimized implementations for all of these primitives. SumCheck is work in progress. There's a couple of hash functions, so few other hash functions are being added. We also want to support multiple fields and curves, because there's typically what I see in the industry is two directions. One is elliptic curve based snarks, and then the second is hash based snarks. So hash based snarks typically use only fields and extensions of fields, as we have seen with Plonky 3 or even binary field based towers of binary field based systems like Binius. And then there's the other spectrum, other end of the spectrum, proof systems like Plonk and HyperPlonk that use elliptic curves. So therefore we wanted Icicle to be able to support all of these use cases. So we support multiple fields and curves. We are in the process of also adding the binary tower fields to accelerate these Binius and even more recent snarks. And as I said, we support 3 languages right now, C++, Rust and Go. So your code can still be in your language, whatever language you choose. And we aim to keep the developer experience very simple, very easy to use, very easy to integrate Icicle. Last point, we want Icicle to be backend agnostic, and we have recently released Icicle version 3 that makes sure that all of our primitives or all of the math that we have implemented, all of the primitives, optimized primitives, should work with any backend. So right now it works with GPU. The plan is to be able to iterate faster to support multiple backends. So we have basically abstracted the software to add new backends and iterate quickly. And the last point, I think this is something that we continuously aim, which is to make it very easy to integrate Icicle in your existing project. So we already have, we are working with a few teams who have integrated Icicle in their own code base for accelerating their snark generation for different use cases. And this is I think the last 2 points are still going to be work in progress, because we want to be able to keep adding new backends. We want to keep improving the developer experience. So if I have to describe Icicle in just one meme, if you don't want to worry about hardware, if you don't want to worry about data transfer, if you don't want to worry about memory management, just use Icicle. Hopefully we keep improving and more people keep using Icicle. I'll talk a bit about architecture to give a sense of what level of abstraction that we are at with Icicle. And the main reason for this is, again, my focus is that we want the developer experience to be as smooth as possible. So what we have tried to do is abstract things at the lowest level possible. For example, we have efficient modular arithmetic implemented, which of course can work on GPU, can work on other backends as well. That is subsumed in elliptic curve group operations. So you also have field operations, group operations for multiple fields and curves. And then if we look at one level higher, we have linear algebra operations, which basically MSM is a linear operation. Entity is an operation that you could think about it as a linear algebra operation. We have hashes. We also support Merkle trees, and the recent update to Icicle also supports custom Merkle trees, because Plonky 3 uses Plonky 3 and also other code bases use very specific types of Merkle trees. And of course, we have vector operations that work with polynomials, and a polynomial is basically like a vector. We also have something called as EC entity. I'm not sure how many of you have heard about this term, but EC entity is like a technique, the operation of entity that you do on elliptic curve points. And then all of this is basically packed in something called as a polynomial API. So when a developer uses Icicle, they don't see any of the abstractions that or whatever happens in the backend. All the developers see is this polynomial API. So writing code from a developer point of view is basically just working with vectors. So if I have to summarize like what we have in Icicle architecture, we have a front end and we have a back end. Front end consists of this multi-language support. By front end, I mean developer facing part of Icicle. And as I said, we try to abstract the complexity as much as possible of these complex cryptographic operations from the developer. And if we talk about backend, as I said, right now we have the CUDA backend for GPUs, which is specifically optimized for NVIDIA GPUs, and we have some work in pipeline that also extends it to the AMD GPUs and also the Metal GPU. Multi-device support is something we have recently added with the version 3, which basically means you can when you as a developer, when you write a Snark prover, you can delegate different parts of your computation to different devices based on what type of proof system you are using. Also, custom backend is also possible. If, for example, a team needs a very specific operation to be accelerated at scale, it's possible to also build a custom backend with Icicle that caters to your particular purpose. So this is like the overall picture of how Icicle architecture looks like. And the bottom line here is, again, we try to abstract everything as much as possible so that the developer can only work with simple vector operations. This is a quick example. I don't need you guys to see the code, but basically what we are trying to achieve is we want Icicle to get at a stage where it's so easy to use, just like PyTorch is for Python. So when you want to do complex matrix operations, vector operations, you just plug in PyTorch, import PyTorch, and you carry on with your coding. That's what we want to achieve for Icicle. We are on the way. It's still improving day by day, but it's already at a pretty decent place. Okay, so we'll start playing around with Icicle since this is supposed to be a workshop. So I'm not sure how many of you already have GPU access, but even if not, Google Colab provides free GPU instance, so we can quickly spin up an instance and try Icicle. There's two things we are going to try, or two things that we are going to, two or three examples that we are going to look at. One is entity, and in entity specifically, there's two versions of entities. Even with Icicle, there's a lot more scope for the developer to handle efficiently handle, let's say, data transfer or parallelizability and so on. So we'll see like a basic entity example. We'll describe a basic entity example, and then we'll see how to make it optimal. And then hopefully we'll also see we'll also take a look at a couple of polynomial API related examples. How do you do division with polynomials? How do you multiply two polynomials, and so on? And then based on those examples, we'll try to do a quick, not a quick, but we'll try to do an exercise to actually write sum check using the polynomial API. Okay, so I'll give line by line instructions on how you can set up the Google Colab instance and how you can integrate Icicle and try to run some tests. But before that, we'll take a look at this entity example that we are going to take. We are going to go over the code. Yeah, I was thinking if we should do like a, we should first set up the Google Colab instance, but I guess we can do it later. So what we'll do now is we'll try to see what do I mean by basic entity and what do I mean by optimal entity, and we'll see both of the examples in Icicle. So let's say you have your host, you have your personal computer or server, and you have GPU device. So it's called host and device. Let's say you have bunch of polynomials on your host, and you want to compute the entity of all of these polynomials. So naively, what you would do is first you take the first polynomial, you'd copy it to the device, you'll send the polynomial to the device, and then you compute the entity on the device, and then the result also needs to be copied back to the host, because your snark prover is basically running on the host. So therefore the result of your entity is being used later somewhere in your snark prover. So you want to, let's say, copy it back to the host. So you do this to and fro. So you did like a host to device transfer, then you did some computation, which is entity, and then you copied from device back to host, and then you repeat that same process for all the polynomials. So this is, so even though you have your entity operations very optimized because you are running it on a GPU, this naive method still is pretty expensive, and roughly the amount of computation that you will do is the number of polynomials times the time it takes for the data transfer to and fro plus the time it takes to compute the entity. So we'll take a look at this example in Icicle, which is basic entity. The question that we want to answer is, can we do better? Can we do better as even as a developer? Can we efficiently handle doing multiple entities without having to do this